All right, chapter 15 covers body composition and nutrition for sport. The word for sport implies that it could be the case that the body composition suggestions and nutrition guidelines that we have for athletes might be different than the regular population. It is, in fact, that the case that according to surveys and self-report, that 50% of the population doesn't do daily physical activity, and 60 to 68% of the population is either overweight or obese. So it could be the case that the athlete's intention and amount of physical activity and the amount of fat-free mass and a body type, it could be the case that the athlete is different than the average individual. And if that's the case, the nutrition and body composition suggestions may be different. Um, so chapter 15 begins with an overview, and we're going to learn a number of different methods for assessing body composition, both laboratory and field methods. We'll also talk about the regulation or the need to monitor potentially body composition in sport, which is going to be different for all sports. Like a ballerina and a gymnast may have very different, or a wrestler and a boxer may have very different body composition goals than a shot putter or a football lineman or whatever. So, body composition is needs to be understood and managed rather than standardized across disciplines. The rest of the chapter talks about types of nutrients and the macronutrients, carbohydrate, protein, and fat, and what they do in regards to fuel to the body. Uh, it discusses the the need for water and minerals and vitamins, and gives suggestions for a diet that an athlete might potentially need. So the caloric values that are listed on all of our food products are based on a 2,000 calorie diet. Our athletes in the gym, although they're young athletes, they're working out 4 hours a day and they're doing strength and conditioning. And when you take a look at their health-calc.com, although it could be .org, I can't remember. When you look at health-calc.com at the energy expenditure and do all the dials, it shows that the athletes are spending about 3,500 calories per day. Um, if that's the case, then that diet there, that suggested caloric intake for an athlete, could be much more than is needed for a regular person who's spending 10 hours behind a computer in a cubicle and not doing daily physical activity. So the athlete's diet could be significantly different than what would be suggested for the average individual's diet. When we're assessing body composition, what we're trying to do is split the body into certain categories or parts, and you could separate the body in regards to its chemicals and its molecules. You could separate the body anatomically, given the individual organs. Body composition is based on a two-component body model. If you go to slide 4, 15, figure 15.1, there is a chemical model, an anatomical model, and that two-component body model that suggests that there are two types of mass. There's fat mass, and then there's everything else that's not fat. So fat mass and fat-free mass. Fat-free mass is going to be muscle, bone, ligament, tissue. That's not fat, so cartilage, all that. So it has a couple of assumptions. Number one assumption is that the density of the fat mass, and hence the fat-free mass, is relatively the same for individuals. The two-component body model is used in densiometry and the other body composition models to set equations and all sorts of different nuances. So if the body is in fact separated into what's fat and what's not fat, then the two-component body model is reasonable. The reason that we want to assess body composition is because just taking height, weight, and age is not enough. In fact, if you take height and weight and you use the body mass index equation, body mass index is only taking into account the actual weight, but it's not what makes up that weight. So somebody who has 200 pounds of fat is going to actually have the same exact body mass index as somebody who has 200 pounds of muscle. So if we're trying to really get a good sense of body composition, then using height and weight might not be satisfactory. So using and then not only that, but this is important because remember the equation for resting metabolic rate is equal to 500 plus 22 times your fat-free mass. 500 plus parentheses 22 times fat-free mass close parentheses. If that's the case, knowing what our percent body fat is going to allow us to understand what our fat-free mass is, and indirectly it's going to allow us to understand what our resting metabolic rate is, and give us a better sense of how to regulate our potential energy in and energy out so that we can regulate weight more effectively. So this is an interesting metric, and we can measure body composition in a number of different ways. Some are field methods and some are laboratory methods. Laboratory methods include densitometry, which is hydrostatic weighing, dual X-ray absorptiometry, air displacement plethysmography, and then skin fold bioelectrical impedance. They can be field methods. Densitometry is what hydrostatic weighing is based on. Muscle is more dense than water, and fat is less dense than water. So fat is going to float on water. The more fat an individual has, the lighter the body weight would be inside of water compared to outside of water, and that's pretty much the basis of the equations. Then the result of hydrostatic weighing is going to be a, an, a body density value for the individual, and then using that body density value, you can plug it into equations and indirectly calculate your body composition. Densitometry is the most commonly used method. It's the most accurate, but there are limitations, as there are limitations to each of the body composition methods. Number one, if you look at the picture on slide 7:15.2, you have to maintain a big tank of water, and that's difficult in order to keep the water clean and pH friendly and this and that. You also need to have a lab that is going to be able to house that particular hydrostatic weighing tank. You have to get somebody to go underwater. Some people might be hydrophobic. You have to get them to breathe out all of the air and stay relatively still underwater so that the machine can do its work. Sometimes people don't feel comfortable being underwater, breathing out all of the air, and so there's a significant stress on the participant there. It's also confounded by a number of issues. Who's to say that everybody's the density of everybody's body fat is exactly the same? So that's going to potentially lead to some internal validity issues, as is the technique itself. It's difficult to get all of the air out of your lungs, and you can't get all of the air out of your lungs because you have residual lung volume. So that's going to be different for everybody, and if that's the case, then there's some validity issues in regards to the calculations. But hydrostatic weighing right now is the most effective, the most commonly used in regards to research. It's just that the lab that I work at, we don't have hydrostatic weighing tanks, so we have to have and provide another option. What are the other options? Well, we could have dual X-ray absorptiometry. That's going to be using X-ray signals that go through the body, and the X-ray signals, very similar radiography, are going to bounce off the more dense material and be absorbed by the less dense material, and you'll get a picture that looks like 15.3b, where increased density and materials that are fat-free mass are going to appear more white than the less dense material, and then calculations can be made to determine body composition. Exactly what those computations are, I'm not 100% sure. DEXA is very precise and reliable, but it's expensive. And not only that, it's putting X-ray signals through a human body, and because of that, it's somewhat more regulated now. I think even you need to have a prescription to do DEXA, and the person who was working on the DEXA machine needs to get certified. And then all of a sudden, there's a cost. You need the lab room, you need the training, you need the certification, you need the times, the time to learn all of that stuff. So DEXA is precise, but needs to be a little bit more user friendly. Air displacement plethysmography, or what's called the BOD pod, is based on, like, if I take my hand and I put it in a pot of water, then the water is going to overflow in the same volume that my hand goes into the pot, and you can get a sense of the surface area of your hand by measuring the volume of water that's displaced. Same thing. The bod pod is a little like a pod, looks like this, and then you kind of open it up and go into the pod. And when you go into the pod, there's a chamber in the back of the pod that has a little a gasket on it. When you go into the pod, air, which is this represents the same volume of air that is the volume of your body, kind of goes out the back end of that air displacement plethysmography pod into like some type of like unit that captures that volume of air, and then you can use that volume of air in calculations to get an assessment of body composition. Exactly, again, those calculations, I'm not 100% sure. In regards to air displacement plethysmography, it's much less invasive, or it requires much less for the subject. They just have to go into this bod pod and sit there for a little while. Unlike the hydrostatic weighing, they don't have to go underwater. You don't have to deal with that. So it seems to be easier to do than hydrostatic weighing, but for the operator, for the person doing the experiment, tends to be more difficult, and it's expensive. You need a lab space. You need to actually have one of those bod pods to do it. You need to have somebody trained in using the bod pod. In our lab, we just don't have one, so we really can't use that. The field methods that we have that are available to us are the skin fold techniques, which is there are many different sites across the body depending upon whether or not you're a Caucasian or African American, or your age, or your, I believe, training status. There's the sites that are potentially used are the thigh, the abdomen, the suprailiac, the chest, the tricep, the bicep, the subscapular. I believe those are the sites. There's probably others, but depending upon the body demographic, more than one or more than three sites are going to be used. The typical three sites that are used when you're using a three-site equation for males are the thigh, the abdomen, and the chest. And for the females, it's the thigh, the suprailiac crest, and the tricep. But if you go onto health-calc.com, I'm just going to call it .com, I believe it's .com, and you go and you track all the way down, there's going to be a body composition app that uses 4 sites, and those 4 sites are the bicep, the tricep, the suprailiac, and the subscap, and those are common for both of the genders. So then what happens is you're going to take the sum of those 3 sites, and you're going to put them into equations or nomograms or into an app on your phone, and it's going to give you an assessment of, or an estimate of, the body composition. Like all the rest of the techniques that we're talking about, these are just estimates. In order to directly measure body composition, you'd have to centrifuge somebody down and separate their parts and see what their body composition is. So all of these things are indirect methods. And it seems as though the skin fold method is relatively accurate. There's a relatively low standard or average error of that estimate compared to the gold standard hydrostatic weighing. So it seems as though skin fold is relatively valid. And as long as you practice the technique and make sure that everybody uses the same technique, it's relatively objective and reliable. So we present skin fold technique in the lab, although the calipers that we have in the lab could be better. They're they're somewhat easy to use, but because the students are just learning the technique, because the calipers aren't the most precise calipers, there's going to be potentially validity issues with the values that we have. So we can always keep practicing, keep working hard. There's nothing that tells you what the skin and the fat in your fingers are going to feel like when you're manipulating the skin to get your calipers situated. So because of that, there's a good amount of practice needed and technical error that's possible. And if you can make your technique more efficient, then the values become more reliable and valid. Anyway, the last one is bioelectrical impedance. Now, they used to have big tables that you have to go on the bioelectrical impedance, but now they have just bioelectrical impedance scales. It cost me $29.99. I used to do the skin fold technique in the gym, but I have so many athletes for them to just step on a scale. It tells them their body composition, their weight, their percent water, fat, their percent water concentration in their body, and also a suggested um, energy in value that they should be taking in terms of calories. And it seems to be relatively easy. What happens is the electrical signal goes into the body and out of the body, and muscle is more water than fat. Muscle is 70% water, fat is 30% water or so. Because of that, muscle is going to conduct the action potential or the electrical signal better than fat. So they just have a current that comes into the body and out of the body, and the scale makes a calculation of the magnitude of that current. And because fat is a poor conductor and fat-free mass is a good conductor, the impedance, which is the slowing down of that electrical signal, will be less if somebody has a higher fat-free mass component. It's reasonably accurate, but the I guess the research is still needed to make sure that the calculations are more accurate. My bioelectrical impedance scale works, but I can only get my age down to 18 when I specify it for each athlete. So my values are somewhat limited to the calculations that we can use to indirectly measure body composition and estimate body composition. So bioelectrical impedance is relatively quick. It's user friendly, but apparently it needs to be more accurate. Figure 15.5. That's the picture of the skin calipers. What's important is that we all adopt the same technique to do the skin caliper technique. That you measure each of the sites carefully. Because it's not only important that I can do my calipers, but it's important that if I perform the skin caliper technique on somebody and then my partner does 10 minutes later, that we get the same results. That's objectivity. It's important that I use the same technique over and over and over so that my results become more reliable. So there's a pretty extensive technique that we'll go over in lab in regards to body composition and using the skin caliper technique. And it's somewhat difficult to do. There's nothing that you can read that's going to tell you exactly what it's going to feel like in your hands and how to deal with somebody who's embarrassed and what you do with somebody who has lotion on their skin or something like that makes it difficult for you to grasp the sites, and what happens if somebody doesn't fit in the caliper because they have too much adipose fat and things like that. So just have to make sure that we go to lab and really study the correct techniques so that we can improve our validity, objectivity, and reliability of that field technique. So fat-free mass is an important variable. Remember that the easiest way to estimate resting metabolic rate and therefore get a sense of energy in and energy out potentially is using that equation 500 plus parentheses 22 times your fat-free mass, close parentheses. So fat-free mass is a good indicator of potentially resting metabolic rate, and if that's the case, it's going to be the starting point for us, balancing nutrition and understanding how much energy in and energy out we need in order to put on hypertrophy and muscle power. But it's also important to potentially increase fat-free mass, because fat-free mass is muscle. So people who are trying to put out more power, more strength, even more endurance are going to have to increase their fat-free mass. And not only that, but they want to have enough carbohydrates so that they don't start using their fat-free mass as fuel. And it's also the case that we do not want to completely eliminate relative body fat or percent body fat, because fat is somewhat important. Individuals who need momentum in their sport, like sumo wrestlers and weightlifters and football offensive linemen, they need mass. Mass times velocity is momentum. They need momentum, so sometimes they need to make sure that they have a relatively high percent body fat, but not necessarily consume fats that are going to cause arterial sclerosis and things like that. So managing fat is more important necessarily than erasing fat. A swimmer could benefit from having a high percent body fat because body fat, like we said, floats on water, and if that's the case, it's going to make it so that the swimmer is more easily able to stay buoyant. So eliminating body fat is not necessarily the object. It's to understand the role of fat in cardiovascular disease and the role of high density lipoproteins in relation to low density lipoproteins and such. So not only that, but all of the lipid bilayers of the cellular membranes, those are all fats, and cholesterols are all fats and stuff. So we don't want to get rid of body fat. We want to manage and understand the individual sport requirements for body fat and maintain those. Many sports are going to manipulate body weight and therefore manipulate body fat to maximize sport performance. Ballerinas and gymnasts and they need to potentially reduce body fat to reduce wear and tear and impact force on the body and to maintain aesthetics. And um, wrestlers and boxers may try to do crash dieting or whatever to cut weight so that they can make it into particular weight categories and things. Or but it's not the case that eliminating body fat is always necessarily going to be good for sport performance. Um, we're on slide 17 right now. Severe reductions in body composition can lead to a number of different problems that are going to lead to a decrease in sport performance and maybe even emotional and psychological um, difficulties. For instance, on slide 18, um, with severe reductions in weight loss comes dehydration, which could potentially impact kidneys, cardiovascular system, and all sorts of other areas of the body. There could also be chronic fatigue, which mirror overtraining syndromes and chronic fatigue syndrome, which is going to potentially reduce performance and reduce concentration and reduce injury. And increase injury. Um, it could be also um, the case that eating disorders develop either because of emotional pressure or physical pressure to lose weight, or just the hyper focus on body composition and it being in the forefront of the athlete's thoughts could and the coaches encouragement could lead to hyper focus and emotional issues with eating and eating disorders. It could also lead to menstrual problems and low iron and other problems associated with malnutrition and such. Bone mineral density could decrease because of severe weight loss and a, an occurrence, especially in aesthetic sports among specifically females, is not specifically, must be females because there's menstrual issues. But when eating disorders and menstrual problems and bone mineral density disorders are present, it's known as the female athlete triad. Um, so it is not the case that what we're trying to do is eliminate fat-free mass. Fat-free mass is also important. Fat is important to for the absorption of fat-soluble vitamins A, D, E, and K. It's important for thermal regulation. It's important to, pad the muscles and bones from impact. So it's not the case that what we want to do is eliminate body fat. What we want is for our athletes to perform at an ideal body composition for them and for their particular sport. Table 15.1 on slide 22 shows the particular or typical body compositions for certain sports. Says that gymnastics is between 5 to 12% body fat. And in the gym, when I use the calipers, I do in fact get those numbers. And when I use my bioelectrical impedance scale, I get numbers from like 11 to 18. And I think it's the case that the gymnastics body type is totally different than the normal individual, and the scale again doesn't let me manipulate the numbers down to lower than 18 years old for each of the athletes. So because of that, I'm not sure that the numbers that I have are absolutely valid. They are relatively valid to the athlete. And then what I do is I train. I try to track body composition to see if I can not predict, but maybe get a little bit of insight into overtraining and things like that. If I notice that fat-free mass goes down, I know that body composition increases, and they're having a hard time sleeping. And I try to put some information together to see whether or not I can put together a trail of information that will tell me. I also take heart rate. I also take that body mass, the basal metabolic rate value that the bioelectrical impedance scale gives me, and I try to just notice any negative trends. In regards to slide 23, how to achieve the optimal weight. The best way to answer that, I think, is to use that 3,500 kilocalories. 3,500 kilocalorie deficit between energy in and energy out over a week is going to lead to a 1 pound in weight loss or weight gain. So if my energy in is more than energy out, it'll be a weight gain. If my energy out is more than my energy in, it'll be a weight loss. And that weight gain could be either fat mass or fat-free mass, depending upon the intensity of the exercise or whether or not that person is doing hypertrophy training or whatever. The suggestion is you don't want to have more than a 500 calorie deficit on each day. So 500 times 7 is 3,500 calories. So the suggestion is that an individual is not gaining or losing any more than 1 kilogram per week, or actually it's uh, one pound per day, 1 pound per week. I think that lose no more than zero point 0.5 to 1 kilogram per week. I think that we want to just talk about that in regards to pounds right now, and because I don't know the kilogram uh, equation, it's divided by 2.2, but it should be 3,500 kilocalories is equal to 1 pound of weight gain or weight loss. And we don't want to exceed more than 2 pounds of weight loss per week. So that's 1,000 calorie deficit multiplied by 7 is 7,000 calories, divided by 2 is 3,500, so 2 pounds per week. So what we want to do is we just want to build these 500 to 1,000 calorie deficits, comparing the energy in and energy out, and we can potentially increase and decrease 1 pound of mass per week. Now, I mean, there's other ways of losing weight. You could completely eliminate carbohydrate from your diet, then you're going to use protein and fat-free mass and lose water weight associated with that. And you'll lose weight relatively quickly. But then because you don't have carbohydrate in your brain's going to get fatigued. You're going to get bored of that diet. You're going to start to eat carbs again. Then the muscle mass comes back, and then you start to increase that weight again. And that's pretty much what yo-yo dieting is. Another way of losing weight relatively quickly is to cut off your left arm, and you'll lose about 5 to 10 pounds. But I mean, there's good ways of losing weight and there's bad ways of losing weight, and we don't want to necessarily eliminate body mass. What we want to do is manipulate body mass and body composition rather, so that we can keep people at an optimal weight. Video 15.1 will give you a different insight into all this. I'm going to move forward. Slide 25. Now we start talking about nutrients, and we go into a different topic where we start talking about macro and micronutrients. Macronutrients being carbohydrate, protein, and fat. Micronutrients are minerals and vitamins. In order for our body to function on a daily basis, most people need about 2,000 calories. 50% of those calories should be from carbohydrate, 30% should be fat, and about 20% from protein. Now, depending upon the activities that an individual is performing, those variables, I mean, those percentages can change somewhat, but should relatively be consistent. If you're gonna do a little bit more endurance training, maybe you increase carbohydrate from 50 to 55% or 60%, and you can reduce protein down to 10%. In any event, your body doesn't store excess protein, so you don't need to. If you have 50% of your diet as protein, you're not going to put on more muscle mass. Carbohydrate is like the fuel for the body, gasoline. So we want to make sure that we have good gasoline. Fat is the storage of energy. If I need to save my gasoline for later, or if I'm low in energy stores, we'll go into our fat stores. And protein really shouldn't be used for fuel technically. I mean, we want to use protein to build tissues and for to build muscles. In terms of training goals, each individual per day needs about 1.2 to 1.7 grams of protein per kilogram of body weight and 3 to 12 grams of carbohydrate per kilogram. So I can give you some information regarding what those values mean, but there are a number of different ways for understanding caloric or intake, or there's the recommended daily allowance, the recommended daily intake. Then there's also the my plate, the my food pyramid, all this. I give my athletes what's called an exchange document, which I believe is the easiest way for me to understand how to put together a a nutritional program. And even if I think if you Googled the word exchange document and diet or whatever, you'll see what I'm talking about. But there's many different ways for estimating and keeping track of your calories. The MyFitnessPal app is a really beautiful way. If you take a look at calorielab.com, or it might be calorielab.org. There's huge opportunities to get information about nutrition and help you keep a an accurate food diary. The nutrients on slide 27 are broken down into carbohydrates, fats, proteins, vitamins, and minerals. Vitamins and minerals are micronutrients, which means you need smaller amounts of vitamins and minerals than you do need the macronutrients. All of carbohydrate is organized from three different molecules: carbon, hydrogen, and oxygen. Actually, elements. Sorry, and then there are more complex and less complex sugars. All carbohydrates are sugars. The simplest are monosaccharides like glucose, but then the sugars get more complex, and you take a glucose and combine it to a fructose, and then you put a fructose on, and then it, more and more and more and more and more. Eventually, what you get is starches and fibers. So you have simple sugars and more complex sugars, but they all get broken down eventually to glucose, and the glucose is used directly by the brain and the central nervous system and the muscles for energy. If the glucose is not used, it's going to be stored as muscle or liver glycogen, or stored even further as adipose fat. But for the most part, carbohydrate is fuel. It helps the central nervous system function, and the muscles use it directly for muscle contraction and energy production. Um, in order for you not to negatively impact your glycogen stores, you need at least 3 to 12 grams of carbohydrate per kilogram body weight per day. And you need to make sure that the athletes maintain that value even if they're not hungry. And for my athletes, it's if they're 12 years old and they're in the gym 4 hours a day, if I do all my calculations, they're upwards. I'll go very low end, 2,500 calories, and high end 3,500 calories for the most part. My older guys are even more, and sometimes they feel as though they're not even hungry anymore. But I mean, we need to make sure that we are encouraging them to eat the correct kinds of carbohydrates so that they can fuel their bodies and not use fat-free mass as fuel. Low carbohydrate diets. If you look at figure 15.8 on slide 30, low carbohydrate diets, which are in red eventually are going to result in a overall decrease in muscle glycogen. A high carb diet, which is about 70% in this particular example, you'll notice that although there are peaks and valleys in regards to muscle glycogen due to acute workout reductions in muscle glycogen, but overall there's a maintenance of muscle glycogen on a high carbohydrate diet. So I mean, at least 50% is what's suggested, and athletes who are training with more intensity or longer duration may have to increase upwards to 70%. It is associated with figure 15.9. High carb diets are associated with a longer time to exhaustion than low carb diets. So, I mean, especially with individuals who are, trying to do longer bouts of endurance and slow glycolytic sports, then high carb diets are seem to be more effective. um, there are many different types of carbohydrates. Some carbohydrates break down very quickly, and when they break down very quickly, like a glass of orange juice, I mean, it gets into your bloodstream very quickly. There's nothing to stop the absorption. There's nothing to stop the breakdown. And because of that, there's a very high increase in blood sugar very quickly, and then there's got to be a very high response from the pancreas in regards to insulin secretion, and because of that, those foods they have a high glycemic response, or are known as high glycemic index foods. Foods like sports drinks, jelly beans, fried potatoes, pretzels, they just break down very quickly and they cause a spike in blood sugar. That could be useful at times. There's other sugars that are less uh, quick to break down. And then there are other sugars that take a long time to break down, low glycemic index sugars. So what we could do is we could potentially like layer our pre-competition meals with some high, moderate, and low glycemic index sugars to make the carbohydrate fuel source last a longer period of time. Um, for just to calibrate your brain, if you take one of those Uncle Ben's boil in bag rice, they have like the perforated plastic, and you just put them in the pot of water for 10 minutes. There's 33 grams in each serving, and each one of those bags is 3 servings. So there's 100 grams of carbohydrate in each one of those bags. So there's 450 calories, or 400 or so calories. So if you multiply the number of grams by 4.1 or 4.2, you're going to get to the number of calories. So one bag of rice has about 400, 500 calories. So I try to use those boil in bag rice as like a calibration for my brain to understand what 100 grams, or about 400 or 500 calories of rice is. One boil in bag rice. Depending upon the exercise time, depending upon the intensity of the exercise, depending upon the amount of carbohydrate that's in the foods that I'm eating, and the GI, or sorry, the glycemic index value of the foods, that has a lot to do with how the carbohydrate is utilized for fuel and how fast that carbohydrate is utilized. For individuals who are doing endurance bouts of exercise, they may want to stockpile carbohydrate, and therefore what they would do is something called carb loading. And in carb loading, what you do is you eventually taper down the activity as you're increasing the amount of carbohydrates, and prior to the competition, you're like stockpiling carbohydrates so that your muscle glycogen values during exercise are are reasonably maintained, or maintained more than normal. Um, Figure 15.10 is a slide that shows the relationship between exercise time and intensity and reduction in muscle glycogen. You'll see that working at 150% of intensity, there's a very, very quick reduction in muscle glycogen. And working at 31%, the red line at the top of the graph, you'll see that there's a more gradual reduction in muscle glycogen. So intensity and exercise time are both correlated with different rates of muscle glycogen reduction. And what we could do is stockpile carbohydrate prior to those bouts of exercise to make sure that we have enough muscle glycogen to complete that activity successfully. There's a video on slide 37 you can go through. The figure 15.11 on slide 38 is an example of two different strategies. One, the red line, ate a high glycemic index sugar prior to the exercise and then conducted the exercise. And you notice that their time to exhaustion was much sooner than the time to exhaustion with somebody who did not preload with a high glycemic index sugar. So stockpiling high index glycemic index sugars just prior to exercise doesn't seem to be a great strategy, but rather making sure that you maintain carbohydrate intake prior to exercise, 2 to 3 hours before exercise and during exercise, seems to be a better strategy. Directly after exercise, it's essential that you reload your body to replace the muscle glycogen and blood glucose losses, and also to make it so that your body doesn't use fat-free mass as its fuel source. It utilizes carbohydrate to fuel the body and uses any protein that you have in that particular post-exercise meal to start muscle growth and protein synthesis. Slide 41 starts to talk about fat. Fat is essential for a number of reasons: thermoregulation, absorption of fat-soluble vitamins. Free fatty acids are an important substrate for fuel. The lipid and cellular membranes are all made out of fat. Steroids have some steroids have lipids in their structure. We do not want to get rid of fat. What we want to do is make sure that people understand what kinds of fats to intake, and understand the difference between high density and low density lipoproteins. Pretty much, low density lipoproteins, they're cholesterols that are so small that they can fit and lodge themselves underneath the cell walls of your blood vessels, and because of that, they start to make like plaque and start to cause cardiovascular disease and arterial sclerosis. And then the high density lipoproteins, they're so big that they can't wedge themselves underneath the endothelial walls. They're actually big enough to knock off the low density lipoproteins and reduce the potential risk for cardiovascular disease. So understanding the impact of the kinds of fats that we eat are more important in regards to our understanding of the utilization for fats. We want to make sure that we have about 30% fat. Fat is a good fuel source. It's a good way to store fuel. You can use free fatty acids when either you're trying to save precious glycogen in your muscles and liver in regards to glycogen sparing. So we don't want to get rid of fat. We want to understand that certain fats cause cardiovascular disease, and we want to limit our fats to about 30% of our diet, and then we should be all right. And that there's only two slides on fat. So slide 43 discusses protein. Protein is very similar in its chemical structure in regards to the carbon, hydrogen, and oxygen, but protein has an extra nitrogen on it. And then in order for the protein to be utilized, the nitrogen has to be taken off. That costs the body energy. So the body is less likely to utilize protein for fuel because of that. You don't store excess protein. So if I want to get bigger muscles and I eat 10 chicken breasts a day, it's not going to work. I only need about 0.8 grams of protein per kilogram body weight per day. And only about 5, 10, maybe even 15% of your daily caloric your energy expenditures from protein in the first place. Protein is broken down into amino acids, And there are many amino acids in green leafy vegetables, so individuals who don't have a huge amount of meat in their diet can still get plenty of the amino acids, and they may just have to get protein sources from beans and legumes and things like that. But protein is essential for muscle growth, protein and tissue synthesis. It's like the metal in a car. Carbohydrate is like the gasoline, and protein is like the actual steel that you make the car with. If you're at a bonfire and you run out of wood, the people are going to throw anything else into the fire. So if you're an athlete and you're running out of carbohydrate, your body's going to use whatever else is there for fuel. So with no carbohydrate left, the body's going to start to use fats and proteins and eat itself away. So I want to make sure we have 50% carbs, but the 20% protein to make sure that we can establish protein synthesis. Higher end athletes, we're on slide 45, want to have about 1.2 to 1.7 grams of protein per kilogram body weight per day. And there's also a negative impact in regards to excessive protein. Um, Taking in more than 3 to 3.5 grams of protein per kilogram body weight per day is associated with various health risks. So we don't want to do that. After exercise, what we want to do is have a carbohydrate and protein rich meal prior to 1 hour after exercise, and that's going to make sure that I have glucose and muscle glycogen for energy and can save any protein and replace any proteins so that I can establish some muscle synthesis and protein and tissue synthesis. A typical chicken breast is going to have 28 grams of protein, um, assuming that there's 100 grams of lean chicken. In 100 grams, 1/3 of that is going to be protein. So 28 grams of protein in a 100-gram chicken breast. There's 6 grams of protein in a large egg. There's 22 grams of protein in 100 grams of salmon. So we should probably have about 3 chicken breasts per day. That'll get me to 100 grams of protein per day. And if that's the case, I mean, in the United States, we, as a country, typically have no problem getting to our daily recommended protein intake. So, my suggestion, especially where I work with younger minor athletes, is that no protein supplements are necessary unless we're potentially talking about like a 17 or 18-year-old athlete who has plenty of testosterone, who's in the middle of a hypertrophy phase during the off season. But I typically won't suggest any supplementation at all. In fact, the only supplements that, according to the research that I've done and the books that I've used to teach classes, the only supplements that are reasonable are things like maybe branched chain amino acids, maybe sodium bicarbonate, maybe ginseng. It seems as though that creatine monohydrate is reasonably safe and functional for strength and power performing athletes like mine, like gymnasts. And the only other supplement that I would never ever suggest for any of my athletes, but that is proven to result in sport performance increases, is caffeine. But I'm not trying to artificially increase or decrease anybody's heart rate in my program. The rest of the chapter talks about vitamins and minerals, and we want to make sure that we have plenty of vitamins and minerals because they're the catalyst for many different chemical reactions. You need to make sure that you have vitamin B for cellular metabolism and ATP production. You need to have vitamin C because it's a powerful antioxidant, as is vitamin E. And we need to make sure that we have plenty of calcium for bone density and phosphorus to help maintain the structural integrity of bone and cellular membranes. We need to make sure that we have enough iron so that we have hemoglobin and myoglobin to help us with oxygen transport. Sodium, potassium, and chloride are all in those the sodium potassium ion channels and all that stuff that helps with action potential propagation and pH balance and things like that. So now we're on slide 51. Water and electrolytes are the next topic. 50 to 60% of the total body weight is water weight. So there's a couple of different reasons why two different reasons particularly why we need to make sure that we're hydrating. Number one is to replace fluids that are lost, and number two is to replace carbohydrate that's lost, and energy that's lost. Um, when you're working in hyperhumid environments where you're going to be sweating a lot, number one goal is to make sure that we keep maintenance of fluid levels and hydrate and electrolyte balance. So, but if you're working out in like a gymnastics facility where the environment is always going to be 72 and relatively the same humidity, it might not be the case that our goal there is to replace fluid loss because our guys aren't sweating a huge amount. It could be the case that what we need our hydration to do is to replace energy and fuel sources. So it's either to replace it's to maintain hydration status or it's to maintain fuel status. Um, I think that one of the things that we want to suggest is by the time an athlete gets thirsty, it's probably already too late. The suggestion is to have small amounts of water or whatever fluid you're drinking so that you don't cause GI upset. Small amounts, frequently, every 10, 15 minutes as opposed to a large amount. Um, um, I mean, I think that okay. So then now we're on slide 64, the athlete's diet. We talk about vegetarian diets. People think that maybe because you're a vegetarian, you're not going to get enough protein. Well, protein breaks down into amino acids, and amino acids are are available in many different green leafy vegetables and all sorts of other stuff. But at the same time, if you are only using a vegetarian diet, you got to make sure your 50, 30, 20 splits are good. You got to make sure that the amount of minerals and vitamins and also amino acids so that you can have protein synthesis are maintained. There's carnitine is another supplement that can be utilized if your ingestion of meat is low and you're not getting enough protein. So the pre-competition meal should have about 200 to 500 kilocalories 2 hours before competition. Potentially have a carbohydrate-rich meal that has multiple levels of glycemic index sugars in it, like a whole grain oatmeal with fruit and honey and milk and or whole brown rice with a little bit of chicken and uh, a little bit of maybe just broccoli or something like that. Um, but mostly carbohydrates in your pre-competition meal. During competition, you want to have potentially 70 grams per kilogram body weight of carbohydrate. 70 grams, yeah, 70 grams per kilogram body weight before during every hour of exercise. It could be the case that if you're an endurance athlete, you're working on stockpiling carbohydrates prior to your exercise training, so you would taper your energy out and start to increase your energy in. That's pretty much carb loading. Um, I don't really suggest carb loading for my athletes because they're not endurance athletes. So I would only suggest carb loading for people who are really concerned with drastic reductions in the muscle and liver glycogen and blood glucose because of long bouts of of activity. The suggestion, though, for athletes is as long as you're maintaining your 50, 30, 20 carbohydrate, fat, protein percentages, you can manipulate those percentages somewhat. Make sure that you're aware of the fact that there's different types of carbohydrates, high, low, and medium glycemic index carbohydrates that could impact your pancreas and insulin sensitivity. And if you're not careful, it can lead to things like type 2 diabetes and other physiological issues. So just maintain the types of carbohydrate. With fat, we want to make sure that we're not eliminating fat, but that we're managing fat and picking the right fat so we don't destroy our arteries. And with protein, excess protein doesn't mean excess muscle. We just want to make sure that we have enough protein at the right time so that we're not utilizing our muscles for fuel. And I think that's enough. I hope that you guys have a nice day. Take care.